Hi, I'm Laren. This is Knife Steel Nerds. I haven't done a question and answer video for a long time. I want to get back into them and do them monthly. So I asked my Patreon supporters for questions. They gave me a bunch of good ones, and I'm going to go through some of the best questions, or at least questions that I am able to answer currently. And some of these are complicated. Hopefully we can get some good answers that make sense to everybody. So let's get into it. All right, the first question is from GZ Custom Blades. Hey Laren, I would be interested in the grain refinement / prequench of high alloy steels. This topic is full with voodoo and not much fact when I read around blade forums or elsewhere. Read some scientific papers as well, but those were focusing on structural steels and others rather than knife steels. I believe there must be space to improve my processes and the outcome as well. To be more specific, I would be interested how to prequench grain refine my preferred steels, Vanitas 4 Extra or CPM 3V. Main goal would be to improve toughness, hardness, balance, and be able to reach higher edge stability with higher hardness and higher toughness at this area. I do my own heat treat with cryo plate quench for all these steels. Okay, first of all, what is prequench? So there were studies done a long time ago, I think in the 60s, where they were exploring something called fish scale grain. And when they looked at these high alloy steels, if they would austenitize them twice, like they would austenitize one time from a high temperature and then quench, and then they would decide they needed to do it again for whatever reason, they would get a lot of grain coarsening and the grain size would get really large. So they did a big study on this, and they found that if they used low initial austenitizing temperatures, that they would get a refinement in grain size when they followed it up by a more normal second austenitizing temperature. So grain refinement is apparently possible, and this might help with our toughness. Now, I have studied this with a couple different steels. One was AEBL. We tried prequenches of 1650, 1750, and 1850 Fahrenheit, and then followed that up with 1925 or 1975 as the final austenitize. Now, when the 1750 prequench was added, the hardness was higher and the toughness was lower. This is because during the initial austenitize, we dissolved some carbide, and so on the second go-around, we didn't have as much carbide to dissolve, so more carbon goes in solution, even though our final austenitizing temperature is the same. So this increases hardness and it reduces toughness. And when I looked at the hardness-toughness balance, even though the toughness had gone down with the 1750 prequench, it did increase the hardness-toughness. So if we look at the same hardness with no prequench, we were either a little bit harder or a little bit tougher, depending on which direction that you look. But when we looked at 1650 or 1850 prequench, there was no improvement. And so it could just be statistical variability that the hardness-toughness balance ended up looking better with the 1750 prequench. Either that, or it is very sensitive to the temperature that we use for the austenitizing in the prequench. Also, when I tested A2 with a 1700 degree prequench, we had to use that temperature or lower because the austenitizing range for A2 was like 1725 to 1775. It showed no improvement in hardness-toughness balance. So whether we're getting grain refinement or not, we're not seeing a clear improvement in toughness. If there is one, it's very small. And so I probably wouldn't dedicate a lot of time to doing a prequench. It's an extra step. It can create some complications, like it's changing your final hardness, and it could be that you're over-austenitizing if you developed a heat treatment without a prequench and then just add in a prequench step. That could affect certain things negatively in certain scenarios. So for me, I think the prequench isn't worth it. And if I were to use one, I would want to do extensive testing to be sure I am getting that small bump in performance. But with a lot of testing that I've done, I'm not sure if we are getting grain refinement all the time. And if we are, there's not much difference between a fine grain and a little bit finer grain. And for a lot of these steels, the toughness is limited by other things like carbides, and refining the grain size a little bit doesn't make much of a difference. Nothing to get excited about anyway. Sharper Apex says, can you share the link? Expected toughness, edge retention, corrosion resistance, and optimal hardness ratings for MagnaMax. Is there a release date? All the deets would be much appreciated. Well, I would love to share the deets if I had them. So we made 2 heats of MagnaMax at Crucible, and Crucible went under. So the final version is being made by other companies like Aerosteel. And we have not yet processed that final material. So we're waiting on it being shipped to Niagara so they can hot roll it, and then I can test it and see exactly how well it does. The release date is supposed to be Q4 2025, but that is right around the corner. So I think there is a small risk that we miss that Q4 date, though we are still shooting for that, and I will let you know how all of the properties end up. It is supposed to be higher edge retention at the cost of some toughness versus MagnaCut while maintaining the corrosion resistance and hardness of MagnaCut. So that is the goal, and initial testing looks very promising with the Crucible versions, but I would like to see how it ends up in the final version, and I can't tell you the release date because a release date is not yet set. So I know this is confusing to many people buying knives because a MagnaMax Mule just came out from Spyderco, so it looks like the steel is out, but that was a prototype heat made by Crucible, and the final version is not yet released. Next, we have a question from Joe Busick. He says, 1.4116 heat treating for achieving theoretical toughness. Is it worth the extra steps versus getting 14C28N or similar? Purpose affordable stainless choppers was something other than 1.4034. Okay, so first we need to define a couple of things that he's talking about. One is, what is 1.4116? That is a common European stainless steel with 50 points of carbon and about 14.5% chromium and some moly and vanadium. 14C28N is a steel made by Alema in Sweden. It has 62 points of carbon and 14% chromium with some nitrogen. Other steels we should compare to are 13C26, which has 68 points of carbon and 13% chromium, and 10C28 Mo2, which is 53 points of carbon, 14% chromium, 1% moly, and some nitrogen. Now, these steels, especially the 10C28 Mo2, are similar in many ways, but there are some important factors to consider. One is that Alema is very, very good at balancing alloying elements and then processing steels to get fine carbide sizes. How do they do that? Well, I don't know all of the secrets, but these alloying elements are very important. So like where 1.4116 has half to 1% more chromium than the 10C28 Mo2, that may not look important to the lay person, but balancing the carbon chromium is extremely important. All of these steels here are riding the line of too much carbon and or chromium. And so any movement up in either element is a danger for crossing that line. And what is that line? Well, if you have too much carbon and chromium, you start to get chromium carbides that will form during solidification. And those carbides, when they form in the liquid, they don't go away. They are very large and they're very stable, and you can't get rid of them with further forging or processing. Now, forging and processing can decrease carbide size. So here is M7 high-speed steel. And when they start out in the ingot, those carbides that form in the liquid, they're very large, and as they forge the steel down, this happens before any knife maker ever sees the steel, the more reduction that it has, the smaller the carbides get. However, these carbides are still large, and they cannot be eliminated. How can I be so sure they cannot be eliminated? Well, we did a study, my father and I, with 154cm AEBL Damascus. AEBL is the same as 13C26. It has very fine carbides. 154cm is a conventional steel with higher carbon and chromium, and it has larger carbides in it when it's made conventionally. And what we did is we started with only 25 layers, but also forged it all the way out to over 3,000 layers, where the individual layer size is smaller than the carbide size in the 154cm. So this steel saw a ton of reduction to an effective amount of the steel only being a micron thick. But the large carbides are still present. We could not get rid of them. Another thing is you can't just get rid of them with higher temperature. So if you heated the steel to just under melting, those large carbides would still be there. They are very difficult to get rid of. They're very stable. They don't go away. And then if you melt it and then resolidify it, those carbides just form again in the liquid because they want to form according to the composition. And holding it for a long time at high temperature is as likely to coarsen the carbides as it is to shrink them. So here was a study on a spray form, Venatus 4. Spray form is a technology that's just a bit worse than powder metallurgy. And their optimal forging rolling temperature was 1050 Celsius. If they went hotter up to 1150 Celsius, the carbides coarsened too rapidly. So the stable, larger carbides, they will grow while the smaller ones will shrink or dissolve. And so you can't just hold the steel at high temperature and get rid of the carbides. They don't go away. So I have seen some cases where people will advertise that they're doing a special thermal processing or a forging treatment to a stainless steel and eliminating the large carbides, but they are not. Those carbides don't go away. And what they're usually doing is cherry picking. So here are images of 1.4116 stainless. I found very large carbides in this steel. Maybe another steel company like Alema could do a better job and the large carbides would not be so big, but this steel had very big carbides in it. But they weren't everywhere. They were scattered throughout the steel. And so I took two micrographs of this steel, one where I found a really big concerning carbide, and this led to poor toughness in the steel. And another, I took a micrograph where that large carbide wasn't present. And so if you want to show people that you're doing this amazing thermal processing that can get rid of ugly carbides that were generated in the steelmaking process, just take a picture where there's no big carbide and tell people that you did an amazing thermal cycling that improved the steel. But for the rest of us, it's better to either use a steel from a great steel company with a good composition that avoids large carbides by and large, or to use powder metallurgy steel. Powder metallurgy is a technology used to keep the carbide size small. So if we had used CPM 154 with AEBL in Damascus, then the carbides would be smaller than with our very extensive forging process. Next question from Coulter Moulton. He says, "Hello, Dr. Thomas. I just recently purchased a second-hand heat treat kiln. Aside from the usual break-in steps, should I take any additional steps to ensure the kiln is working properly? Are there any pitfalls that I should be wary about?" Now, I'm not an expert on furnace maintenance. That'd be a better question for the furnace manufacturer. But one thing you could do if you're worried about the performance of the furnace is to check the temperature with a secondary thermocouple. So there's one that I use from ThermoWorks. It's a flexible ceramic thermocouple, so you don't have to drill a hole into a furnace or anything. You can just snake it through the door. And then you can loop it around something in the furnace to make sure it doesn't come into contact with the coils, and you can measure the temperature. And that also can be used to measure the temperature fluctuation throughout the furnace, such as away from the control thermocouple that the furnace is reading. And so you can see that the furnace thermocouple is measuring the same as your secondary thermocouple and be confident that it is functioning correctly. And so here is a chart that I took. I took a bunch of measurements of my even heat furnace with a secondary thermocouple, and I found that the furnace thermocouple would reach the temperature, but at the floor of the furnace, it would take some time for the furnace to fully equalize and reach the same temperature as the furnace thermocouple, which was at the ceiling of the furnace. So that was interesting and useful. So most of the time, everything is good, and if the thermocouple is functioning, it's reading approximately the correct temperature, and everything is good. But checking with a secondary thermocouple, you can see, is everything operating how it should? Next question from Arthur Herbst. He says, "Hello, Dr. Thomas. Why are the recommended tempering temperatures for stainless steels often as low as 300 degrees Fahrenheit and as short as 2 times 1 hour, while in non-stainless steels, especially low alloy steels, it is usually at least 350 degrees Fahrenheit and a duration of 2 times with 2 hours each? Do stainless steels suffer less from reduced yield strength from under-tempering?" Okay, so we need to talk about a bunch of things. One is why are stainless steels recommended 300 degrees and 2 by 1 hour, while low alloy are 350, 2 by 2 hour. Those are not recommendations that look like things I typically give. If anything, it's often the reverse, where I will give shorter tempering times for the low alloy steels. And I have recommended as low as 300 degrees for low alloy steels and high alloy steels. Typically, I don't recommend any lower than 300 for anything. But there are certain steels where you need a certain minimum tempering temperature to get a big jump in toughness. One example would be 15 and 20, where at 350 degrees Fahrenheit tempering, we saw like 40, 50 foot-pounds, and 300 degrees, it was much, much lower. Now, there was higher hardness, with the 300 degree, but you're kind of giving up that amazing toughness you can get with 15 and 20 by only tempering at 300 degrees. Other steels have lower toughness to begin with, and so their increase in toughness is often more linear. So 300 degrees can make more sense. But on the subject of time, temperature is more important than time. So here's a chart of 1080 steel. That's a simple carbon steel. And if you compare 205 Celsius, that's around 400 degrees Fahrenheit, with 30 minutes versus 2 hours, it's a difference of like half to 1 Rockwell C. So usually the temperature matters more. So as we go up to 315 Celsius, that drops it like 4 or 5 Rockwell, a much bigger difference than tempering over twice as long. But another factor with tempering time, especially with high alloy steels that are given a high temperature temper, like at 1000 degrees Fahrenheit, 520 Celsius, is that short hold times do not convert the retained austenite. And that is one of the things we're trying to do, is reduce our retained austenite during tempering at those high temperatures. And so if you're only tempering at 15 minutes or 30 minutes, even with multiple tempers, 3 tempering cycles, there's still a significant amount of retained austenite, where if you do 1 hour or even better 2-hour tempering, you can reduce the retained austenite almost to 0. So that's one of the things that is happening during the tempering cycles, is not just softening the steel, but you're also converting retained austenite, and that takes time to happen. And different steels, this conversion will happen at different temperatures. So here we have a high alloy steel up top, and at 400 degrees Fahrenheit, it still has all of its initial retained austenite. That is with long hold times and multiple tempers. And you don't start getting significant reductions in the retained austenite until much higher temperatures, like 500, 530 degrees Celsius. Where with a low alloy steel, this one is sort of similar to a 52-100, there's a big drop in the retained austenite by tempering at only 400 degrees. And this is why you need multiple tempers. So he said 2 by 2 hour, for example. You do it again because you converted a bunch of retained austenite to new martensite, and so you have to temper again to temper that new martensite. Now, what was the thing he mentioned about reduce yield strength from under tempering? So here are charts from S5 and S1 tool steel, and it has yield strength, tensile strength, and hardness. Yield strength is how much stress a steel can take before it starts to deform. So if you pull on a piece of steel and let go, it goes back to the original shape. If you pull it more and let go enough to deform it, then it won't go back all the way to the original shape. You can think of it the same with bending rather than pulling. And the tensile strength is if you pull it all the way until it breaks. That's the limit of the material. And tensile strength and hardness are often well correlated, but yield strength sometimes is not as well correlated with hardness. So you can have a high hardness, but the yield strength, how much stress the steel can take before it deforms, is lower. And so you might be tempering very low to try to get a high hardness and a high tensile strength, but the steel is not as difficult to deform as you'd think it would be based on the hardness. And so if you temper a bit more, you get an increase in yield strength. The hardness and tensile strength does go down a little bit, and your toughness also improves. So this is why I give a minimum amount of tempering, because you want to increase your yield strength and gain more toughness. And so if you under temper, then that may not happen. Now, as of the question, do stainless steels suffer less from reduced yield strength from under tempering? No, I wouldn't say so. But it's hard to get data on this. They just are not testing this very often compared to hardness and toughness experiments. So I can't give a big comparison between a bunch of different steels. All right, a question from Ron Swisher. Does carbon migration occur when any steel is forge welded to another steel? Are there different percentages of migration? Does it occur when welded to nickel, to non-magnetic stainless? All right, this question is not so easy to answer. But the thing he's talking about with carbon migration is that if you forge weld 2 steels together, especially in Damascus, if one has high carbon and the other has low carbon, the carbon is going to diffuse from the high carbon steel into the low carbon steel. And how much diffusion occurs will depend on the temperature and the time and how thick the pieces are. You know, if they're inches thick and they're welded together at one point, then the amount of diffusion that occurs is going to be relatively small in percentage terms. If we have a high layer Damascus, the layers are very small, and so the time for the carbon diffusion is relatively short. So here is a study done by Howard Clark and John Verhoeven, where they did some estimates using simulations, computer models, to look at how long it would take for carbon to fully equalize in Damascus with different layer counts. And so they found with 2,000 degrees and a 200-layer Damascus, that's 3/16 thick, that it would take 2.7 seconds for the carbon to equalize in the steel, so very fast. Now, other elements take longer to equalize. So at the same 2,000 degrees, looking at manganese instead, it takes over 48 hours for the manganese to equalize in the steel at 200 layers. Oh, carbon is a much smaller element, and so it diffuses relatively quickly. But will carbon always completely homogenize, reach the same carbon content between the two layers? Not always, no. Even if the layer count is small. So there's a famous equation by a metallurgist named Darkin, and he took a steel with high silicon and a steel with almost no silicon with about the same carbon content, 44 to 47 points of carbon. And when he held it for a long time at high temperature, he found that the carbon was diffusing into the low silicon steel and away from the high silicon steel. So the silicon had changed the interaction between the steels so that the carbon was preferentially going to the low carbon steel. And different elements can have different effects. So silicon is the strongest for making carbon diffuse away. Chromium has the opposite effect, where it makes carbon want to go towards that steel. And so if you were forge welded up to a non-magnetic stainless, that just means a stainless with high chromium and nickel, the carbon would diffuse preferentially into the stainless steel. So there would be even a little bit more carbon diffusing into the stainless. And this can be an issue because those non-magnetic stainless steels, like a 302, 304, these are called austenitic stainless steels, they don't have any carbon in them, and they're designed not to have any carbon in them. And so when you're getting a bunch of carbon diffusing into it, that can cause issues with the high chromium content. And when we've looked at AEBL 302 or 19C27 welded to 302, we find large carbides in the 302, even though there were no large carbides in either the 302 or the AEBL to begin with, and that reduced the toughness. Now, he also asked about forge welding to nickel. This is a common thing that bladesmiths will do, is that they put a pure nickel sheet in between a high carbon and a low carbon steel to try to prevent carbon diffusion. So does this work? Yes, it does. So the solubility of carbon in nickel is much lower than iron. So solubility, that means how much carbon can diffuse into the metal. Nickel is much lower than iron. The diffusivity, how fast carbon diffuses in nickel, is about the same as iron, but the solubility is much lower in nickel. And so nickel works very well as a carbon diffusion barrier if you want to avoid carbon diffusion and equalization. One more example of times when carbon does not fully equalize. So I talked about AEBL 154 cm Damascus earlier. So the AEBL has 68 points of carbon and 154 has 1.05% carbon. So you'd think those would fully equalize and end up with the same carbon content. But remember also that there are carbides that stick around at high temperature in the 154 cm. And so those carbides aren't going anywhere. Instead, it's the carbon that is still in solution that equalizes, and that would be about 82 points of carbon for 154 cm. And so the 154 cm is only going to lose about 8 points of carbon, and the ABL will gain about the same amount. So yeah, in that case, the carbon diffusion is quite small, even though there is a significant carbon difference between the two steels. Okay, Joshua Heller, what steel is next? Would you consider making a high alloy, non-stainless, high edge stability steel? Or is that space already fleshed out? Okay, that's a lot of terms. High alloy, that means that it has significant amounts of chromium. The alloy content is greater than 5%. Non-stainless, the chromium is not so high that it's a stainless steel. High edge stability steel. Edge stability refers to a balance of high hardness and high toughness, because for an edge to be stable, it has to avoid both chipping, which is controlled by toughness, and deforming, which is controlled by hardness. So you want a steel with high hardness and high toughness. So looking at high alloy non-stainless steels, the highest combination of hardness and toughness that I see would be 64 Rockwell CPM1V. That is a non-stainless steel with very low carbide content, very high toughness, relatively low wear resistance, or maybe medium low wear resistance. And so that steel is pretty good. So would I make a better one than that? I'm not sure. Now it can also go to lower hardness, and also you can see Z-Tough on here has 61.5 Rockwell with higher toughness. So maybe there are certain edges that benefit more from toughness than from hardness, and so this type of regime would be better with a bit lower hardness but significantly higher toughness. Now, could we go even higher in hardness than 64 and maintain high toughness? That becomes more difficult. Maybe we could design a steel specifically to optimize toughness at 65 or 66 or 67 Rockwell, or a steel like my Apex Ultra maintains pretty decent toughness at 67 plus Rockwell. And would there be design opportunities for something in that higher hardness space while maintaining some toughness? I don't know. I don't know what the limits of that would be. Based on this trend line with CPM1V, at 66 Rockwell, we probably couldn't get any higher than 10 foot-pounds or so. And would there be a benefit to that? We wouldn't really know until we were able to test that steel. And we'd have to test it in different types of edges and under different types of tests to see if it worked. So CPM1V would probably be my choice for that, though CPM1V gets very little use in the knife industry. So it wouldn't be so much that I would have to develop something as I would need to convince people that this is a good steel in knives. And that's not really for me to decide. That is for knife makers and knife users to decide that that is something they want. Now, there are some other steels out there I haven't tested. One is ASP 2012 from Aerosteel. It also is a low carbide volume steel, but its data sheet shows it getting to 63.5 Rockwell or so it gets no harder than the CPM1V. So maybe it has a bit better properties. We wouldn't know until we test it, but it's not in a completely different realm of properties. It would be roughly similar. Last question from Zach. Are there any alloys you are interested in developing that aren't specifically designed for use in knives? Well, my day job is developing automotive sheet steels. I don't really talk about that on this channel, but for example, here is a patent application which is publicly available for you to read if you wish, on an advanced high-strength steel there called an automotive sheet steel that I developed. And so here's my name, the inventor, Laren S. Thomas. You'll have to guess in the comments what the S stands for. So this is an 1180 megapascal steel. That is a tensile strength. We were discussing tensile strength earlier with high ductility, hole expansion, bendability, and formability. So this is an example of a product that I have worked on. And automotive sheet steels are totally different than knife steels. For example, they are low carbon steels. We care more about things like formability and ductility for a given strength level rather than toughness specifically. And so, it's all about being formed in complex parts and then being able to handle welding and also crashes in cars. And so they have different types of microstructures. Often we want retained austenite, unlike a knife steel where we're usually trying to minimize retained austenite. So totally different and interesting in their own way. I just don't want to do a whole video on automotive steels for a channel about knife steel because people probably won't care. But if you want to learn more about automotive steel, then let me know and I will think about it. That's all of the questions that I have the energy to answer right now. So if you would like to ask questions for the next Q&A video, please join us at patreon.com/knifesteelnerds. So people on Patreon get to join the community and we talk about stuff. I put out early articles and videos on there before anyone else. And there are certain articles that are also exclusive to Patreon. Like all of the information about MagnaMax that currently exists is on the Patreon because I don't want to have a public article about the steel before it is publicly finally released. But there is some initial information on the Patreon. So if you would like to ask questions in the Q&A, come to patreon.com/knifesteelnerds. But until next time, I'm Laren. This is Knife Steel Nerds. Bye-bye.